guys, welcome to today's tutorial on Thevenin's theorem. So today we'll be learning about how to use the Thevenin's theorem to analyze an electrical circuit. So Thevenin's theorem is also saying that if I have an electrical circuit, a two-terminal circuit, I can represent that circuit by its equivalent circuit. So we have a linear two-terminal circuit like this. A circuit which has two terminals. Alright, so these are the terminals of the circuit. So I have built a circuit like this. So in this circuit, I have a voltage, a resistor here, another resistor, another resistor. So this is the circuit that I have built. So this is a two-terminal linear. It has two terminals here. So at this terminal is where we can connect any load to the circuit. This circuit is fixed, it is not changing. The values here are not changing. So we can connect a load, that is an iron, a fridge, a microwave, hot plate, whatever we want. We can connect it towards the terminals of this fixed circuit. So we can say this is what our load resistance is, a variable load. It can change with time. Maybe with time it can be an iron, it can change towards a microwave. Its resistance value can change. So that is what our load here, the variable load. So Thevenin is saying that if I have this and I want to calculate the current through the load resistance, the load here, if I want to calculate its current, we now know that the portion here, this portion of this circuit is considered to be fixed. It doesn't change, it is fixed. So Thevenin is saying that we can represent or replace this fixed portion of the circuit by an equivalent circuit. We are not going to include our load. We are just focusing on the fixed portion of the circuit. We are going to represent it by an equivalent circuit. And in that equivalent circuit, we just need two things. We need the Vth, a voltage source. Every circuit has to have a source. So in that equivalent circuit, we need a single source, which is called the Vth. That's a Thevenin's voltage. And we want an equivalent resistor value, resistance, which is called Rth. So Thevenin's is all about finding your Vth and the Rth for the fixed portion of the circuit. The fixed portion of the circuit. So after calculating your Vth and your Rth from the fixed portion of the circuit, you are going to draw the Thevenin's equivalent circuit. And the Thevenin's equivalent circuit is the Vth, which is connected in series with your Rth. So you draw Thevenin's equivalent circuit of this circuit here, and it should be a voltage source, which is the Vth. It is connected in series with the resistor value, the Rth. So Thevenin's equivalent of this circuit here is that. Now we realize that in this circuit here, we've connected a load to the terminals. So after getting its Thevenin's equivalent, we can now bring back our load here, the load that we removed, we didn't consider. We are now going to connect that load to the Thevenin's equivalent and find the current through that load using the equivalent circuit. So I can now connect my load that I removed, I didn't consider. I can now connect my load to the Thevenin's equivalent circuit and then calculate the current through that load using this equivalent circuit. So that current will be produced by the source, which is I. So we know that this Rth and this RL are connected in series. So if I want to find the I moving through the RL, it is going to be Vn over R. But the Vn we are talking about is the Vth. So I have Vth over the R we are talking about is these two in series. We are using the Ohm's law. So I have Rth plus RL in series. So that will help you get the current flowing through your load using the Thevenin's theorem. So let us go over. Thevenin's theorem is all about representing a fixed portion of a circuit by its equivalent circuits. And in that equivalent circuit, you just have to find two things. Find your Vth, find your Rth. When you find those two, you drop the equivalent circuit, but they should be connected in series. So we have the voltage source connected in series with the RTH, and now you bring back your load that you didn't consider in this circuit, that load that you removed. You bring back that load and connect it to the terminals of the equivalent circuit. Then you find the current or the voltage for the load using this equivalent circuit. That's all Thevenin's theorem is about. So now our job here is to know how to find the Vth and the Rth. So one thing you should also know is that when we are going to find the Vth and the Rth, we are first of all going to remove the load from the circuit. We are going to solve the Vth and the Rth for the fixed portion of the circuit only. So it means we have to remove the load from the circuit. So in this diagram, this is the load. They will tell you the load you have to work on. That is the resistor you are finding its current or the voltage will be your load. So we have to first of all remove the load from the circuit so that it will be left with only the fixed portion. So in this diagram, you need to remove your load from here. So if I remove my load, it means this portion becomes what? Open. You don't have any elements connected here. So that open portion where you remove your load is where we are going to find these two elements. The Vth and the Rth are going to be calculated at this portion. So we will first of all calculate what? Our Vth here. Then later we will calculate what? Our Rth at the same portion. Okay, so Thevenin's theorem just states that a linear two-terminal circuit can be replaced by an equivalent circuit which has a voltage source Vth in series with a resistor Rth, where the Vth is called an open circuit voltage. Why is it called an open circuit? It is an open circuit voltage because where we are going to find that Vth, that portion has been open circuited. You remember I said we remove the load from there. So if we remove the load, this portion becomes open and we are finding the Vth at that portion. So the Vth is an open circuit voltage. And the Rth is known as the Thevenin's equivalent resistance at that same open place. So one thing you should also note is that when we are finding the Rth, there should be no source in the circuit. You should see no source. We are finding the total resistance, the equivalent resistance in the fixed portion. So our job here is to focus on what? The resistors. We don't want to see any source, either voltage or current. So Rth deals with only resistors in the circuit. By finding your Vth, you have your circuit as it looks like. Your voltage and your resistors will be there. Then you use it to find the Vth. But Rth should only be calculated when resistors are in the circuit. We don't want to see any voltage source. So with that knowledge, you will use that theorem here to solve this question using the Thevenin's theorem to calculate the current flowing through the 4 ohms resistor. We will go through the steps one by one because this is our first example. So in the videos to be uploaded in the tutorial 2 and 3, we will be solving more complicated circuits than this. So let's go through this question together. So we are going to use the Thevenin's theorem to calculate the current flowing through the load, which is what? The 4 ohms resistor. So in this diagram, we first of all have to calculate our what? Thevenin's voltage and our Thevenin's resistance. So between the two, you can decide to calculate any of them first, the one you want. You can decide to work with the Vth, then later work with the Rth. So let's say we are going to work with what? The Vth first. So what is our load? Our load is what? The 4 ohms. If the question says calculate the current flowing through the 4, meaning your focus is on the 4. So that is your load. So first thing to do is to remove the load from what? The circuit. Remove it from the fixed portion, which means all this portion here is what? The fixed. This one is fixed. It is this one which is our load. So we are going to remove this portion from there. So let's say we've removed the load and we've placed it somewhere here. 4 ohms. We've placed it somewhere. So let's draw the circuit and see what is happening without our load. So I have a voltage source. I have these 2. I have this 6. I have this 8. I have what? This 10. So now this is where we had the load, so we've removed. And now we are going to find what the voltage Vth at this portion. So we write Vth. So let's write our values. 10 ohms, 8, 6, 2, and what? 28 volts. So we are going to look at this diagram here, use this circuit to calculate the voltage, and that voltage is known as what? The Vth. So let's see what is happening. Now, when you draw this circuit, you can use any methods you've learned so far to calculate your Vth. The Thevenin's theorem here is to find Vth. So the method or the approach you use to get the Vth, we don't have anything called the Thevenin's maybe approach. Thevenin is all about finding Vth and Rth. So you can use any approach, whether series, parallel, node, voltage, mesh, and you can use that one to get your Vth. Just know that your Vth should be correct. So let's see how you can find Vth. We know that voltages have what? Polarities. Vth is a voltage source, so it should have polarities. So it can have plus and minus. You can have plus here, minus here, or plus and minus here. So for this case, you can choose an arbitrary direction. Let's say here is our plus, here is what? Our minus. So let's see what is happening in this diagram. If I have a current being produced by this, the current will be moving from here. When it gets here, what will the current do? It will split here and here. So when this one also gets here, what will the current do? The current won't split. It will pass through this 8. Why? Because we have this branch. This branch here is what? Open. This branch is 10 ohms, but its portion here has been open circuited. Don't forget there is a voltage we are trying to find, but don't forget that that same portion has been open circuited. So there is no current going to flow through what? This 10 ohms resistor. So it means we are going to neglect the 10 ohms resistor. Alright. So you can see that this Vth is a voltage source. You can do it like this. Bring an arbitrary or imaginary lines like this. It's a voltage source. Now we can see that this 8 ohms is connected in what? Parallel with the Vth. This 8 ohms here is connected in what? Parallel with what? The Vth. This element, the voltage here is 0, so we are not going to include it. So this 8 and the Vth are connected in parallel. And we know that elements in parallel have the same voltage. So if that is the case, it means the voltage across the 8 here is the same as my Vth. I don't know my Vth, but I can relate that the voltage across my 8 is equal to what? My Vth. One other thing you can do is that if you want to find your Vth, consider a loop where your Vth is part of. There are several loops in this diagram. I have a loop here, a loop here, a loop here. The whole portion here is also a loop. But I can consider the small portion where the Vth is making part of. That is this loop. Alright. So let's say if I take this loop and I want to write KVL in this loop, what will happen? If I want to write Kirchhoff's voltage law in this loop, what will happen? It means I will need the voltage here, together with my what? Vth. I'm trying to see what the Vth will give me, but I'm using the idea of what? KVL in the loop. So if I'm writing KVL here, it means I need the voltage here, and the voltage here. So let's assume that the voltage for the 8 is called VA, the voltage for the 10 is called what? VB, and yes, this one is what? The Vth. So let's write our KVL equation. We are moving clockwise, and we know that the current through this 8 is moving down from here. The current is moving down, so we have plus, minus. The voltage here is what? What's the value of the voltage here? Is 0. Why? Because we realize that no current is flowing here, so the current here is 0. 0 times 10 will give us 0 volts. So we are going to consider VA and Vth in this loop. So in writing our KVL, realize that we move from negative to positive. So I have what? VA. Now the Vth, I'll move from where? Positive and leave the negative. So I have minus Vth is equal to what? 0. So from here, if I make Vth the subject, means my Vth is going to be what? Is equal to what? My VA. So we are using the idea of what? KVL to calculate for what? Our Vth. So we've seen that our Vth value is going to be what? VA, and VA is the voltage across the 8 ohms resistor. So your job here is to use this circuit here, calculate the voltage across the 8, which you know that it is the same as your VTH. Very simple. So first of all, identify what your VTH will be equal to, then use the circuit to solve for that voltage, which is the same as your VTH. So we are going to use this diagram to get what? The voltage for the 8. So let's see again. The current flowed here, split between 2 and 6. When it goes here, it didn't split. The current flowed here, meaning this 8 and this 6 are connected in what? In series. We are not including the 10 because we realize current is not flowing. So it is off. Forget about the VTH now. We've now seen that the VTH is the voltage for the 8. So forget about it. Use the circuit as you see here and calculate the voltage for the 8. So you've seen that 8 and 6 are in series. From here, I know you would get it very simple because you know your network reduction. So we have this, we have that. So this is my 28 volts, my 2. So my 6 plus what? 8 in series is giving me what? 14 ohms. Our job is to get voltage for the 8. So if I need for the 8, I have to focus on what? The 14. And from here, all the elements are in parallel. So they have the same voltage. Meaning the voltage across the 14. Voltage across 14 is also what? 28 volts. But the 14 is from where? 8 and 6 in series. So if it is in series, it means I can apply the voltage divider rule to get the voltage for either of these two resistors. But I'm interested in the 8. So I'm going to use the voltage divider rule between 6 and 8 to get the voltage for what? The 8, which is my VA. Because I've called that voltage VA. So my VA voltage divider between 6 and 8 is going to be what? 8 over 6 plus 8 times the voltage they are sharing, which is the voltage for the 14. And that one is what? 8. So what do we get from this one? I have 8 over 6 plus 8 times 28, which is giving us 16 volts. So the voltage across the 8 ohms is 16 volts, and we deduce that VA is the same as our VTH. So now it means my VTH is also what? 16 volts. That's the first thing you have to do. So now we've managed to calculate what? For the VTH. The next thing to calculate for is what? The RTH, Thevenin's equivalent resistance. And as I said, in calculating for Thevenin's equivalent resistance, there should be no source in the circuit. It means the sources that are already given in the circuit, we have to turn them off. And we know from superposition that when we are turning off a voltage source, we short circuit. When we are turning off a current source, we open circuit. Very simple. So we are going to apply the idea of the superposition we did here. Good. So this is our main diagram. This is the question. So this is where we remove the load. We found the what? VTH. At that same portion, we are going to clear the VTH, then write RTH. Still, it remains open. We will clear the VTH, write RTH, turn off all the sources in the circuit, then find the equivalent resistance. Okay, so let's see. Now I have a single source, so it means I have to turn it off. And if I'm turning off a voltage source, what do? I have to represent it by a short circuit. So that portion becomes short circuited. I have my resistors there. This is my 2. This is what? 6. This is what? My 8. This is my 10. And this is where I'm going to write what? RTA. So 10, 8, 6, 2. Very simple. You see, there should be no source in calculating the circuit. For calculating what? The RTA, there should be no source in that circuit. So when we get here, we are trying to find the equivalent resistance here. That's the RTH. So what you can do is that just assume you are looking in this direction. Alright, just assume that if you are looking in this direction, assume that there is a current moving on the branch here. You are going in this direction. So if there is a current moving on this branch, how will the current move? The current will move through this thing. When it gets here, current will have to split here and here. Meaning these two are in what? Parallel. But you are not done. Just move and get to the end of the circuit. It's similar or it's the same as calculating total resistance here. So we can't just stand here and analyze. So let's move to the end. So the current through the cells will get to this junction. Abi, you are happy now. So when we get here, we have what? A short circuit. Whenever I see a short circuit, I become happy because it makes the work simple. So when the current gets here, since there is a short circuit, a branch with no resistor, the current will avoid these two, then move on through this branch here, then get backwards to where your source is. Meaning this 6 and this 8, we are not including this. So this 6 and this 8 are connected in what? In parallel, because the current splitted here. So you do this and that in parallel. Let's call it RA. So RA is 6 by 8 over 6 plus 8, and that is giving us, we have 6 this over what? 6 plus 8, which is giving us 24 on what? 7 ohms. So that is the equivalent of these two. And we know that this and this in parallel is going to be in series with the 10. You already know how to do that. So it means our RTH is what? RA plus the 10, which is 24 on 7 plus 10. And that one is giving us 94 on what? 7 ohms. So that is our RTH. RTH. So we've managed to calculate VTH and what? RTH. Now the last thing to do is to draw your Thevenin equivalent circuits of this. And that one, as if you remember, I said it should be a voltage source, the VTH, in series with your RTH. So just draw a simple circuit. Your VTH in series with what? Your RTH. So this is the RTH here. This is what? The VTH. They are in series. That's a Thevenin's equivalent of this. Now the question was asking us to calculate the current through the load. So after drawing the Thevenin equivalent of this, we are now going to bring back the load that was connected at this terminal. We are now going to connect the load to the Thevenin equivalent. So we are connecting the load here, and that is RL, which is the 4. You remember we removed the 4. So we are going to find current in the 4. Very simple. So current in the 4, I is what? V over R. So the V is VTH over what? The R there are 2, RTH plus RL. So VTH is giving us 16. RTH is what? We had 94 on 7 plus the load resistor, which is what? 4. So it means our current here is equal to, let's punch it together, it's equal to 16 over 94 on 7 plus 4, which is equal to, so the I is equal to 56 on 61, and that one is equal to 0.918 amperes. 0.918 amperes to be what? Our I naught. So we've used the Thevenin's theorem to calculate current for the load resistor 4 ohms, and we had what? I naught. So take your time, go through the video again, know how to calculate your VTH using the KVL approach here. Assume or consider the loop your VTH is part of. Write your KVL and see what your VTH will be. Then go back to the main circuit and calculate for the voltages you need. Then you come and find the what? RT. By finding RT, there should be no source. So if you see a voltage source, you have to turn it off. If you see a current source, you have to turn it off. Calculate your RT, then draw your Thevenin equivalent. And the Thevenin equivalent is a voltage source, the VTH, in series with the RTH. That's the Thevenin equivalent. So if you need the current for the load, then you bring the load, connect it to the terminals, then use your Ohm's law. I is equal to V over R to calculate what? The current through the load. So this is the end of tutorial 1 for Thevenin's theorem. Thank you very much for watching this video.